Alrighty, so we're going to talk about a MEGR today, or insulation resistance testing. I've got some slides here from Boeing Charlie Works course. I'm going to run through some of these just kind of at a high level. But to understand MEGR insulation resistance testing, I think everybody on here has at least used one before. But I'm going to give you a little bit of background, a little bit of theory behind it, and then we'll do. Even though you guys have probably put hands on, we're just gonna do a quick demonstration, and then I got a short video for you at the end. So the so in the whatever years of aviation, and I found this out too. Like when I first started at FEMA, and first really started doing consistent troubleshooting, is I'd go out and troubleshoot a wire, and I would do power and ground and do continuity and test the wire. I'm like, the wire's good. And I get so frustrated because they wouldn't find anything else and they would change a wire and it would fix the problem. I'm like, well, this is a bunch of crap, because if I can't check a wire and know and be able to find well, what good is what we're doing? And really what they found is that traditional electrical testing that they've been doing for years and that they talk about in the books, they're really only going to find about 20% of the problems. Okay, so there's really been no inspection manuals to detect intermittent opens and shorts. There's been no procedures. Electrical failures are about 25% of all unscheduled maintenance, so it's obviously a very important thing. Wiring testing is obviously reactive most of the time. Really, we're not doing many health checks on that, so we wait until it breaks, and then we go out and try to find what the problem is. Okay, so there's really three different types of wire faults. Open circuit, simple. The current's not flowing, the wire is completely broken. The circuit's completely broken. Then there's a short circuit where the circuit bypasses the load and goes directly to ground or another wire, like a wire-to-wire chafe or a pin-to-pin short, what have you. And then a ground short. So the insulation has broken down and it's causing the conductor to short to ground, such as chafed wiring the structure. Okay. So the traditional FIM multimeter test, the FIM tells you to go out and do these wiring checks. It's only effective for about 20% of the faults. So 80% of the faults, these are intermittent opens or shorts that only occur in flight, vibration, temperature, pressure, all this other stuff that our normal wire checks the FIM tells us to do don't account for. So Boeing Charlie Works especially, they've been focused on this for years. Since I started working with them, 7-8 years ago, like their troubleshooting methods have drastically changed. Every year I would go to their course and it would be new techniques and new equipment and new whatever. And honestly, every time it gets a little better, it gets a little bit easier. One of the challenges being is nobody knows this information. The stuff is actually in the maintenance manual now, and we'll go through that in a little bit, but the information is just not getting out there. So hard faults, 20%, that's what we already talked about. Firm faults being like high circuit resistance, so that the bite test fails, but you do the FIM wiring check and the FIM wiring check passes. So what do? They throw a box in or whatever, but it may still be a wire short that the current type of wire testing is not finding. And then the soft faults are going to be like 10% of the faults out there. Those are the really hard things to find. The slight variation on the ground, but those are the ones where it faults in flight, but it gets on the ground and everything tests fine. So coming up with ways to find these problems, to find these issues and fix these problems is what this is all about. So here shows a lot of the new intermittent wiring checks. They're all in the maintenance manual. They go through it all. We're only going to focus today on insulation resistance testing. Okay. So insulation resistance, really what it is, low voltage measurements such as continuity, they can't detect insulation damage or moisture, right? So the insulation damage of the moisture allows the circuit to bypass the load, goes directly to ground or another wire. Some of the stuff we're going to talk about today, so we currently have a Fluke 1587, and that is our insulation resistance tester that we have at the stations. Some of the information they're going to talk about in here is going to talk a lot about electrical pressure and decay checks. We can do some of that with ours. Some of this is more structured to the Megger MIT 2500, and we'll discuss that a little bit later too. So some of this information may look a little bit different than what we currently do. So insulation resistance checking, what we're basically doing is we're putting electrical pressure into the wire. Okay, so same as you pressurize a water line to see where it's going to leak. That's what we're doing. Why do we need to do this? So, and I think any of us that have used a Megger to try to find faults, we're really putting electricity in that wire and trying to get it to jump a gap if there's a fault in the wire to tell us that that wire is faulted. The problem with that is when you go higher in an aircraft and the air pressure gets less, the electricity can jump a bigger gap. Also, there's pressurization in the plane, and the pressurization in the plane makes everything in the plane move. So if you see this little chart here, really what this is showing is how much voltage it takes to jump a distance. Okay, so if you see here, that's only 2/10 of an inch. And for me to jump 2/10 of an inch, I need to go almost 12,000 volts. So that's a lot for 2/10 of an inch. If the aircraft's moving, the wings are moving, all this stuff, it's going to be really hard to find those faults. The most that our current insulation resistance testers go up to is 1,000 volts. We're going to discuss that a little bit too. So there are tricks to get around that. If we know there's a fault in the wire and we really can't find it, we can go to Walmart and get us some helium and just take helium and kind of run it down the wire with the Megger going. And if there's a fault, you're going to see it because it's going to jump far. Even at 1,000 volts, it's going to jump. So it's a really cool way to find it, but not something we would normally do. So here's some of the differences that you're going to see, right? This, if I remember right, this fault was on a 3.7. After they found the fault, they did some testing just to show the examples here, right? So here's the chafing. This is above the cockpit door. It's just some trim pieces. This is where it ended up chafing. You can see where it cut through the wire. When I believe they took the plane up. I don't think it was pressurization. It could have been, so I don't want to lie to you there. But at 15,000 feet, you can see that gap has dropped down some. That this is where it was. They had taken this plastic piece off when they found the wire because it rubbed right through there. When you get to 25,000 feet, that piece is laying on here. And if you go all the way up, that aircraft's at 37,000 feet, you can see there's almost pressure pushing that wire bundle onto here. But the problem is you come back down to the ground, the pilots are like, yeah, we're getting this problem in flight. During cruise, we got whatever light or whatever it is, and we go and do meg test, we do all this stuff, and we can't find it because our gap has changed. So in order for us to do that, we need to put more voltage in or get a bigger Megger, right? So some of the other things we can do with megging is we can check wiring and components at the same time. Now, there are limitations to this, but if we wanted to check anything on the plane that has a coil, such as a motor, a transformer, resolver, synchro, LVDT, anything like that that has a coil, we can check the wiring and that coil at the same time, usually from the rack. So you pull the rack out, you put the pins in, going through any component, you cannot go more than 500 volts DC. Just keep that in the back of your mind. But it makes an easy way to find faults, but also just do a health check, and you can see, if you haven't even get ready to go bad. Some of the problems in the past, Meggers have been around a long time. They've had these crank Meggers. They've had other types. Usually you push the button, put some voltage into it, and it kind of came down to tribal knowledge. There really wasn't any manuals that said, hey, you know, here's the limits. If you hit the button, here's the limits. It was kind of like an art. You know, you had the old guy that would crank the old meggers up and put it on there. Oh yeah, that's bad. But there's really no instructions or limits on how to do that. So Boeing has done tons and tons and tons of testing, especially Charlie Works, and they put together limits for us so that we know going through, you know, we do an insulation resistance test or we, you know, a meg test. We know that, hey, is this value good or bad? You know, I don't know. So now we actually can look in the manual and they have directions on for us to do it and go through and actually tell us what the limits would be. Now I disagree a little bit with the limits, but we can go through that later. I've seen what they're saying is that at 500 volts with the insulation resistance tester, anything less than 50 mega ohms would be bad, and at 1,000 volts, anything less than 100 mega ohm would be bad. I'll be honest, at 1,000 volts, I've seen things 300 meg that are definitely causing faults. You know, if you see something that's if you're not finding any other issues and you see something that's not optimum or really close to it, and we'll talk about those limits later, I would definitely focus on that area. So I was talking about we have AMM. If we went to the AMM and we went in chapter 20, there is a section in chapter 20 that talks about intermittent wiring inspections and checks. This is all the stuff that gives you instructions in this chapter in the maintenance manual, and you can use as a reference when you're going through and do your testing to sign off your test or whatever it is, even if it's good. So insulation resistance test for years and years and years, it was kind of, I think there was one reference to using insulation resistance testing or meggers, and it was always you were limited to 1,000 volts. Now recently, Boeing has done testing and they have gotten their engineering department to up that for us. So now we are legal to go up to 2,500 volts. So anyone that's done this testing, the meggers we have, unfortunately, right now only go to 1,000. But there are the one specifically that you will probably come across. I think Atlas has a couple. Is the MIT 2500. That one does go up to 2,500 volts. Maybe I'll do a class on that at some point. But if you need more, call me and I can walk you through on how to use that. So when you're using meggers, insulation resistance testing, a lot of safety stuff you have to worry about. Okay, now it's not going to kill you. It's not even going to hurt you. It will wake you up. You know, don't hold the test leads. Don't touch them. You know, don't use damaged test leads. All that easy stuff. But really, you're going to go, oh shit, yep, I got shocked. But it's not going to do anything to you. The biggest things you have to worry about is A, don't use it. Any wiring that goes through fuel tanks, it is not for that. That is, you use different test equipment. If that wiring goes anywhere inside of a fuel tank, you do not use a megger. That is 100% big no-no. Also, one of the most important things of checking wiring is to look at the wire diagram first and make sure you're not going to meg through something you shouldn't be megging through. And we will talk in a moment on how to make sure that we're doing that correctly. So limit-wise, we talked a little bit about that. 500 volts DC. If I'm megging at 500 volts, the limit's 50 mega ohms. If anything 50 mega ohms or less, we would call that bad. 1,000 volts DC, anything 100 mega ohms or less, we would call that bad. Again, if I've got something 150 mega ohms at 1,000 or even 200, I'm sorry, there's something going on with that wire, and I'm going to investigate that further. And if we have 2,500 volts, we're going to jump up to 250 mega ohm or less. Really, if we're using the MIT, we're going to use a different measurement. And I'll just touch on that, but really that measurement, which these values are based on, is 10 microamps of leakage rate. Okay. The MIT 2500, you can actually see the leak rate, and if it's anything above 10 microamps, again, our stuff, so we won't really go into that, but our stuff doesn't show that measurement. A lot in the past, the Megers, guys, you hit the button, do an instant test. Okay, yep, looks good. Good to go. We really are using more of time tests now. This picture shows the MIT 2500. This shows the setup for it. I'm going to go through our time test with the one that we have, and we'll get into that with the demonstration. When we're doing insulation testing with wiring only, the tests that we want to do. So you're going to disconnect the cable, the cable from both ends, the wire bundle from both ends, the cannon plugs from both ends. You're going to check wire to wire. So if you have multiple wires to check, you're gonna do a different meg check for each of those wires to each other. You're gonna do a meg check from each of those wires that you're testing to ground. You also want to do a check for each of those wires to the back shell or the connector itself. A lot of our connectors are shielded. So that shielding, the wires could be shorted to the shielding and not actually to the airframe somewhere. And you're not going to see that if you disconnect this and you don't check it to that back shell. You only check the ground. So if I go through and disconnect this end of the cable and this end of the cable, and I'm checking all my pins to ground and it all looks good, but this thing's shorted to the shield and the shield goes between each of these, that shield has no way to get to ground. So we definitely want to make sure we're going wire to wire, we're going each wire to ground, and each wire to the back shell of the connector or the shield wire if it's there, if it's easy to get to. Okay, so examples at 500 volts, especially with the one we use, 550 megaohm would be a perfect score, if you will. 1,000 is going to be 2.2 gigaohms. But our limits that we're looking for is like this one here on ours, 85 megaohm. He's only testing at 500 volts. So per our limits, if we look at this, anything less than 50 megaohms, that technically would be good. There's no way in hell I would call that good. I'm sorry. So I disagree with a little bit of their limits, but some of that is going to be, the more experience you get doing this, the easier it's going to be to read these numbers. Okay. And like we talked about a little bit earlier, we can meg through components only up to 500 volts DC. That does not mean boxes. That only means anything with a coil, such as a motor, resolver, RVDT, that type of thing that has something with a coil in it. When you're testing those, you're going to test from the coil to ground. You don't need to do wire to wire because technically, you look at the wire diagram, they're all connected anyway. But you'll be able to test, if you want to test the wires and this at the same time, you would go through and put one of your leads on ground, the other one on the wire, and you would test it. And like I said, no more than 500 volts, and see what your reading is. But that's going to check the wire. It's also going to check the internal of that component if it's shorting internally. Okay. And if you need to go higher on the wires, you would obviously disconnect the component, and then you can go up as high as your meter will go. In our case, 1,000. Okay. So what does this look like practically? Let's jump over. Okay, this is our 1587. This is the one we have at all our stations. If you took the multimeter class, I went through and described what all this stuff does. This has two functions. First, it acts as a multimeter, and then it also acts as an insulation resistance tester. Okay, multimeter side, you would put your leads in on this side, turn it on, go to whatever function it is. Something I usually do is I go to ohms and I check the resistance of the circuit that I'm going to do. So I do two checks, especially when I first start testing. The reason we do this is if I see anything in here at all, I got to really make sure that my wire that I'm going to test is not going through a component somewhere, such as a box or what have you, because you really shouldn't see anything involved here at all. Okay. So insulation resistance testing is all done from this side. So your red, it's marked positive and negative. Your red's going to go on the top. Your black's going to go on the bottom. Even though it's colored red, black's going to go on the bottom. And you're going to turn to this section. Now, right here on this section, you can see I've got 50 volts. That would be my test voltage. Okay. This section here is going to be the amount of voltage it's putting through the wire. And if it's shorting, the amount of voltage it's taking for it to short. And this is going to be my actual reading. Now, right now, the way it's set up, 50 volts, if I push and hold the button, it's doing a test. You can see it says test. You can see the little lightning bolt, which means it's testing right now. And for 50 volts, that would be a perfect score. It's not shorting to ground at all, 55 megaohms, okay? Our normal process now is, instead of just holding the button, we're going to use this here. We're going to select either pi or DAR. They are basically the same thing. DAR does a test for a minute. So if I push that button, it's going to run through that test for a minute, or until it sees a stable reading that does not fault. So if I were to hit this now, it's going to go through and test what it does. It's called a dielectric absorption rate testing. That's what DAR stands for. It's really going to take the first 30 seconds, put it over the second 30 seconds, and give you a reading. We don't need to really worry about that DAR reading. What we're going to do is we're going to hit this, we're going to test it, and really what we're looking for is we're going to count to about 10. If our reading jumps right up to whatever the max for that is, and you can unplug the leads to see what the max is and go through all the settings. But if it jumps right up to the max, I can be fairly confident that there's no fault in that wire at that voltage, or maybe my leads aren't even there, because what it's saying is basically I have an open and I don't have any type of a connection between my two. Okay. Hit the button again, that turns the test off. So every time you do a test, when you're going to a new connector, you looked at the wire diagram, you said, okay, I know it's pin 2. So you're always going to do your first test at 50 volts. 50 volts, if you accidentally shoot through a box, is not going to hurt the box. However, if you see something at 50 volts, if it shows anything up, you better damn well make sure that you have everything disconnected you should have. Otherwise, you're going to fry something. So 50 volts is a fairly safe way to go to start. Now I know I have nothing there. I'm going to bump it up, whatever it is. If I'm going through anything with a winding, such as a pump, whatever it is, if I'm just doing wiring, I can still jump up to 500, give it a test. The max value I'm going to see at 500 is 550 megaohms. I see that. That's basically showing me it's a perfect test. Give it about 10 seconds. It's not changing. I'm going to stop the test. If I'm doing strictly wiring, I'm definitely going to go up to 1,000. That's the highest this one will go. So I'm going to hit that test button again. It's going to go to 1,000. I'm going to turn it on. The most you're going to see at 1,000, a perfect score, is 2.2 gigaohms. Okay, so I'm not seeing anything there at all. Again, give it about 10 seconds to make sure, but that looks good to go. So let's see what a bad reading looks like. So now I'm going wire to wire. Okay, pin to pin. So again, I'm going to start at 50 volts. Okay, I don't see anything. I'm not going through a box. All good to go. So now I know my setup is good. I'm going to bump it up. Let's go to 500. I'm going to test our wire. Oh, 500 looks good. Well, maybe we have a good wire. Let's go to 1,000 just to make sure. Okay, I'm going to bump it up to 1,000. Oh, I'm seeing something at 1,000 that I didn't see at 500. So what it is the voltage that I have, and it's actually shorting out. It's saying it's shorting out at about 200 and some volts DC, but at 500 volts, it did not jump that gap that I have in here. It took it to 1,000 volts. So you can't say, oh yeah, I tested at 500, it's good to go. You don't know. Even at 1,000, If I have a suspected wire, if I'm testing this for a known fault and I went through the wire diagram, I'm like, man, it's got to be like one of these wires. And even at 1,000, I don't see anything. I may want to see if I can get my hands on that 2,500 megger, because it may not be jumping the volt, just as we saw the difference in here between the 500 and 1,000. Okay. And same thing if I were to go my black lead to ground instead of wire to wire, same exact thing. So let's give you a little more example, and it's going to show you a little bit on the MIT 2500. I've got a video to show you. Take about 5 minutes, and then we'll be done here. So. Do you guys hear the sound?
No, I have not.
And an insulation resistance fluke meter. And we're also going to use the ultrasonic devices here to look and find our leak by visual and by listening as well.
Right, so we have a scenario here where we're looking for a short to ground or short wire to wire. So I'm going to connect the negative lead of the device, the Megger, up to the ground. I'm going to turn the meter on to 50 volts. We always start with 50 volts to ensure that we don't accidentally connect to the wrong pin by visually looking or getting on the wrong pin using the schematic. I simply press the device for 5 seconds, and I make sure that I'm above typically 50 mega ohms. I'm good. It's greater than 10 gig. Now I can ramp up to 500 volts. I'm going to hit the test of 500 volts. And again, I'm looking for greater than 50 mega ohms. I'm at 5.3 gigs. I'm good. That was pin to ground. Now I'm going to move pin to the wire next to it, 55. So 53 to 55. Again, 50 volts. I'm going to press the test, and I'm looking for greater than 50 meg. Well, I see it climb to 52 volts, but it's not greater than 50 meg. It's actually about 8 meg and moving around. That tells me that we have a condition where there's leakage, electrical current leakage together. So now this is great for testing because it just pulses current. It was what we call clamping. It was preventing excess of current, and it protects an LRU. If I accidentally tied into a device like a command computer, it would have protected it and not damaged it. However, it's not very conducive to identifying the exact electrical arc condition where I need ultrasonic.
So what he's going to talk about now is we see the fault. We put our meg around there, and we're like, yeah, we got a fault, but where the hell is it? Okay. The only thing we really have available to us now, what he's going to show you is acoustic imaging camera. Atlas does own those, and we know for a fact, I think we've checked them out before in Miami. I don't know if there's one in Baltimore, but this is the easy way to do it. The other way to do it is we take the newest guy on the crew and we have him go wiggle the harness hand over hand, and someone watches the meter, and that's where the pi setting, where the DAR pi button that we talked about, the pi setting comes in handy, because DAR goes for a minute, but pi goes for 6 minutes unless it doesn't see a fault. We know we have a fault. We hit the pi button 6 minutes. Someone watches the reading. The other person goes hand over hand and wiggles the harness, and you watch for that reading to change. When that reading changes, you know you're close to your fault. Now, if we're going to cheat and use the cool stuff, unfortunately, we haven't talked Mike into buying one of these yet because it's 20 grand. But you're going to see him use this acoustic imager and how we can find electrical faults with this acoustic imager. Okay.
So we're going to tie into the fluke megger, which provides a solid, steady pulse I'm going to turn the meter on, select installation resistance, 500 volts. And now we're ready to press the lock. The lock is going to hold it on to 500. We're pressed. I can see that it's not able to get to 500 volts. It's at 318.7 meg. Now Derek can simply sweep the aircraft.
All right. So now that we have a continuous signal from our meter, I'm going to use my sonic imaging device, and I'm going to sweep this area, and I'm going to look for any areas of interest. Now I'm going to zoom in here a little bit. I'm going to look for my leak. Oh,
so he's moving his frequency range right there.
Yes. I'm adjusting my sensitivity to get my correct range, get rid of any noise. And right here, I'll sweep around, and I think I'm going to see something. I have some returns right in this area. So now that I've identified an area of interest, I want to pinpoint it with my ultrasonic test probe. And I'll get this set up. And the ultrasonic test probe is going to help me locate the precise location of my leak by listening for ultrasonic frequency, an electrical leak, if you will.
Now, Atlas does have this as well. This is called a UL 101. You can take that acoustic imager he was talking about, and let's say we have and I've seen this in person, let's say we have a wire fault that we found. It's in the wings somewhere. Let's say it's a 4/7 leading edge. You can open the flaps up, and from the ground, you can see the approximate location of that fault. It's pretty cool. And then if we really want to get specific, we can grab one of these UL 101s and get right down to the exact location. That acoustic imager is going to get you really close. You can always do that and then do the shake test as well.
So now I will sweep around. And I know my area was here, my area of interest. And I'm getting a nice audible signal, the loudest right in this area, right here. As I sweep away, the sound kind of dies down. I can hear it on my headset. The sound dies down. And right about here is where I have my loudest tone. So I'm going to look for some kind of fault in this area. I'll probably break the bundle apart and start looking for some kind of fault. I want to be careful, though, when we want to stop our testing.
Yes.
Before I do that.
To make sure it goes out, too.
Yes, yes.
Go ahead
Okay,
and put it on there, and it should go silent when I stop the test.
I just lost my tone.
Yep.
Yes.
And then I can hit the button again, and the tone will come back. It's one way to validate. All right, stop.
Okay.
And that's it. That's a very easy way to not only detect, we like to say fish finding with this, and then fish catching with the fluke.
Okay, that gives us a pretty good idea on how to do this. I just gave you guys a whole ton of information. What kind of questions we got?
When can we get some of these new meters?
Well, we have the one, right? The MIT 2500, I'll be honest, we were kind of holding off on that because the TPI, the company that we've been getting these new meters, they're coming out with a Mega this year that's going to go up to 3,000, but it's also an LCR meter built in. I'll talk to Mike a little bit, but I'm pretty sure Atlas has the MIT 2500. I think we talked to them a couple years ago and they bought some, but we can definitely, maybe I can talk a lead from each station to check in and see if they actually have those in stock at the station. We can kind of go from there. What else you got?
Hey, so what are the risks with sending that much voltage through, like a 22 gauge wire versus like a 16 gauge wire?
Not going to affect it at all. The amperage that you're sending through is going to be about the same as what the doing a continuity test with a multimeter is. It's going to be like a 1 to 5 milliamp range. So it's not the amperage. You're just hyping up the voltage really high so that it jumps. It's not. Again, we don't want to shoot through boxes, but it's not going to hurt wiring at all. If we get to the point where we're doing, right when you start getting close to 3,000 volts, if we have to use that, if we ever get the equipment to do that, we need to D-pin connectors because 3,000 volts, it will start shorting between pins in the connectors. But I think that's why they limited it to 2,500 in the book. There's been a few jobs I've been on where I had the MIT 2,500. I tested it at 2,500, couldn't find any faults, did everything. They brought Charlie Works out after the fact. They had this big thing that actually goes up to like 10,000, but they went up to 3,000. Actually, they went to 2,750, and they found the fault at 2,750. But I never would have found it with the equipment we had. So it is what it is. You know, you use the techniques you have and hope you can find it. Anybody else?
Hey, did you talk about no megging through fuel tanks?
About no megging through what?
Fuel tanks.
I did. Yeah, we went through safety on megging and what to do, what not to do. There's got to be more questions. I know John's got a question. That or he's not paying attention.
No, I mean that was everything was pretty smooth on that one. I mean,
Okay,
I'm really
so-
impressed with seeing some of those other meters, and I'm actually looking really excited to the next time we have to do some megging.
Well, I told you guys before, you know, we've discussed this in the past that, hey, Atlas has that acoustic imager in stock there. And there's been a couple problems. Actually, I think I had you guys go check it out, and then we never got to the point where we used it. But that is one way to do it. There's multiple ways to get to the same, to find the same thing. However, we're trying to give you guys the easiest, quickest path to do that.
I wish you'd have never showed them this ultrasonic imager.
I know. That's why I waited this long. I waited almost a year to show it to them.
Oh, I'm itching to use it now. Now I'm just
Well, you think I get upset about tire pressure gauges? Fuck one of those up.
That's why we're Atlas has two in Miami. We already know that because we've already put hands on. So I don't know if Baltimore has one, but I know for a fact Miami does.
Yeah, I definitely think we'll just use Atlas's equipment on that.
Yeah.
But it would, I think it'd be really cool just to utilize it so we could all train and see with it in person, and just get a little feel for some of that test equipment.
I'm gonna be back down there within the next few weeks. Maybe we can go check it out. We can do some training on it in person.
Hey, Mike, that goes to that old adage, man. You know what the best aircraft to have is? Your neighbors.
Yeah.